Hey everyone, and welcome to today's Explainer. We are jumping right into the absolutely fascinating physics of light. Let me tell you, by the time we wrap this up, you're going to look at the world around you in a completely different way.
Okay, just think about this for a second. You walk into a totally pitch black room, right? You literally can't see a thing. But flick a switch and boom, instantly the whole room is visible. The wild part here, light itself is actually invisible as it travels through the air. You honestly can't see the beam at all unless it actually hits something. It's really just this incredible form of energy that strikes objects, bounces off them, and then hits our eyes. And that is exactly what allows us to see the world.
And man, does it move fast. Like unbelievably, mind-blowingly fast. Out in a vacuum, light travels at a staggering 3 × 10⁸ meters per second. Yeah, you heard that right. 300 million meters every single second. I mean, that is the ultimate cosmic speed limit, hands down. And honestly, it really sets the baseline for everything we're going to dive into today.
So, here's our roadmap for today. First, the magic of light. Second, bouncing back, light reflection. Third, spherical mirrors explained. Fourth, rules of ray diagrams. Fifth, bending light, refraction. And finally, demystifying refractive index.
Section 1. The magic of light.
So the very first crucial thing to understand here is that light exhibits what we call rectilinear propagation. Sounds fancy, I know, but all it really means is that light travels in completely, perfectly straight lines. Like a very dependable friend, it just goes straight. Unless it hits a physical boundary, it doesn't curve, it doesn't zigzag, it just shoots straight forward.
Section 2. Bouncing back, light reflection. All right, so reflection is simply the bouncing back of light. Picture throwing a tennis ball really hard at a wall. It smacks the boundary and bounces right back out. Light does the exact same thing, and it follows 2 very strict rules when it does. First up, the angle of incidence is literally always equal to the angle of reflection. Always. Second, the incoming incident ray, the outgoing reflected ray, and that perpendicular imaginary line we call the normal, well, they all sit perfectly flat in the exact same plane.
Section 3. Spherical mirrors explained.
Now, moving from flat walls to curves, it's actually super simple to remember the 2 main types of curved mirrors if you just picture a standard, shiny soup spoon. Look at the inside of the spoon. It's curved completely inward, right? Kind of like a cave. Well, that's your concave mirror. Now flip that spoon over to the bulging backside. Yep, that is your convex mirror. And here is the really cool part. Even though the surface is physically curved, those exact same laws of reflection we just talked about, they still perfectly apply at every single tiny microscopic point along that curve.
Section 4. Rules of ray diagrams. Okay, I know ray diagrams can seem a little intimidating at first, but hey, I am right here with you. It all boils down to just 4 basic rules of geometry. Rule 1. If a ray comes in parallel to the axis, it reflects straight through the focal point. Boom. Rule 2 is just the exact reverse. If it passes through the focus first, it reflects out parallel. Simple, right? Rule 3, if it goes straight through the center of curvature, it reflects right back along that exact same path. And finally, Rule 4, if it strikes the center pole, it bounces off at the exact same angle. See? Nothing to stress over, it's really just geometry.
Now, if you take a look at the nature column on the right for this concave mirror, you'll see a really interesting pattern. For almost all positions, the image is real and inverted. What that means is the light rays actually meet up in the real world. They're just upside down. But, and this is where it gets kind of wild, if you move the object incredibly close, like right between the pole and the focus, the rays actually spread apart. So your brain sort of hacks the system, tracking those rays backwards to form a virtual and erect image, meaning it looks upright, it's totally enlarged, and it appears to exist entirely behind the mirror in this sort of dream world.
Section 5. Bending light, refraction.
All right, shifting gears from bouncing light to bending light. The main takeaway here is that refraction is quite literally just the bending of light. But you gotta wonder, why does it bend at all? Well, it's all about speed. Remember that 300 million meters per second speed limit we talked about? Yeah, light only travels that fast in a pure vacuum. The second it enters a new medium, like air or water or glass, it actually slows down. Imagine you're sprinting full speed on pavement, and then you suddenly veer into deep beach sand at an angle. Your body is going to pivot because one leg gets bogged down in the sand before the other one does, right? Well, light does the exact same thing. When it changes speed, it is forced to change direction.
To really visualize this, let's look at a totally classic physics setup, the rectangular glass slab. This is honestly the absolute perfect way to see refraction in action. Just notice how the line of light enters from the top left, bends, and then exits down at the bottom right.
So let's actually trace this journey step by step. When the light enters from the rarer air into the much denser glass, it hits the brakes, it slows down, and as a result, it bends right towards that imaginary normal line. Then it travels straight on through the glass. But watch what happens when it hits the other side. Upon exiting the glass and popping back into the air, it speeds right back up, which makes it bend away from the normal. And the absolute coolest part? Because of this double bend, the final exiting ray ends up being exactly parallel to the original incoming ray. It's just shifted over a little bit.
Section 6. Demystifying refractive index.
Now, just like reflection, refraction comes with its own set of strict rules. The first one should sound pretty familiar by now. The incoming incident ray, the bent refracted ray, and the normal line all live flat on the exact same plane. But the second rule, well, that's Snell's law. It states that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant for any given pair of materials. Now look, please don't let the word sine scare you off. I promise it's not scary math. It's simply a rigid rule of nature that tells us precisely how much that light is going to bend. And that constant number we get at the end, that actually brings us right to our final big concept.
Think of the refractive index simply as a measure of a material's strength. If the light and the material were arm wrestling, this number basically tells you how strong the material is at forcing the light to slow down and bend to its will. We calculate it by taking the speed of light in a vacuum and dividing it by the speed of light in that specific medium. So what's the bottom line? A higher number simply means a denser material, much slower light, and a much sharper bend. Seriously, it is just that simple.
And honestly, that just brilliantly illustrates the physics of reflection and refraction. We've taken light from a perfectly straight line, we've watched it bounce off walls, mapped out its crazy geometry on curved mirrors, and finally, we measured its sheer strength as it bent its way through solid glass. But you know, wrapping all this up leaves us with just a massive, incredible thought. If light dictates absolutely everything we are able to see, what else out there in the vast, deep universe is currently hiding just out of sight, just waiting for us to build the perfect lens or mirror to finally bend it right into view? Keep wondering about that one. Thank you guys so much for hanging out and learning with me on this explainer today. Catch you next time.